Okay, this is a nice review paper. It's really long. Very nice to read, though, by a bunch of really good authors who have been working on Western disturbances for a while. They talk about recent developments in Western disturbances and climate variability. I am going to try my best to extract the most salient points after having read it, because if I cover the whole thing, it'll take forever. But even with this brief introduction or brief summary of this paper, is going to take several podcasts, I suspect. It doesn't matter. Let's just try to go through it. The abstract starts with some nice details. It covers, the history of Western disturbances research, ideas of tracking them, the track density, their interactions with global modes, their modeling history, their predictions, and then ends with some future science questions, questions that are still not answered properly. And basically, they place each section in the context of what the literature has done so far, what is reported in the literature so far, and what is new. So, especially because one of the co-authors had written a review recently. I think he also wrote a book on it recently. As you notice, I usually don't put the author list on my podcast. I put the information in terms of the DOI, etc. I don't know why I have this habit of not showing the authors. There's nothing special about it. It's just maybe I want to focus on the content and not so much on the authors, but nonetheless, Western disturbances are synoptic scale weather systems embedded within the subtropical westerly jet. They are cyclonic systems. They are often referred to as being originating in the Mediterranean, but they are different from the regular cyclones, their intensification processes, vertical structures, etc. And there are many details. So I'm just going to take all the figures and try to make the points and not read a lot of the text. Okay, manifesting as upper level troughs, often associated with a lower tropospheric low. Over the western and northwestern India, they share some dynamical features with extratropical cyclones. So they are not exactly same, but there are some common features. And you notice these when they come and start producing climate variability and extremes and summer and winter precipitation and so on over western and northern India. And India cares a lot about the Western disturbances. WDs, as we'll call them, Western disturbances, are most common during the boreal winter, so December to March, during which they bring the majority of precipitation, both rain and snow, to the western Himalaya as well as to the surrounding areas of North India, Pakistan, and the Tibetan Plateau. So they can go around to the Tibetan Plateau or come towards the south into northwestern India and Pakistan and so on. WDs are also associated with weather hazards such as heavy snowfall, hailstorms, fog, cloudbursts, avalanches, frost, and cold waves. To the extent that they are cyclonic systems, it's not surprising that they are causing these things. In the paper, we review recent developments in understanding WDs and their impacts. Over the last decade, recent studies have collectively made use of novel data, novel analysis techniques such as tracking algorithms and the increasing availability of high-resolution weather and climate models. This review is separated into 6 main sections: structure and thermodynamics, precipitation and impacts, teleconnections, modeling experiments, forecasting at a range of scales, and paleoclimate and climate change. So they look at various periods of the Holocene to see what we know in terms of WDs and climate change, but I'm not going to go into those details. Each of the section is motivated with a brief discussion on the accomplishments and limitations of previous research. So they start with a summary of previous research and highlight the limitation before going forward to say what is new. A number of step changes in understanding are synthesized. Use of new modeling frameworks and tracking algorithms has significantly improved knowledge of WD structure and variability, and a more frequent approach can now be taken. A more frequentist approach can now be taken. Improved observation systems have helped quantification of water security over Western Himalaya. Convection permitting models have improved our understanding of how WDs interact with the Himalaya to trigger natural hazards. Improvements in paleoclimate and future climate modeling experiments have helped to explain how WDs and their impacts over the Himalaya respond to large-scale natural and anthropogenic forcing. We end by summarizing unresolved questions and outlining key future WD research topics. That list is quite long, almost 30 I think, so we'll read them all because I'll capture the main gist of the model of the review better than anything, just in terms of your own collection of information on WDs and what remains open in terms of the science questions. I'm struggling to keep my foot elevated here because I have sprained it and the swelling is just coming down, but I still have to keep it elevated. Okay, let's start with the introduction, which is brief according to the paper itself. I'm not cutting anything out here. The Indian subcontinent experiences 4 distinct seasons. The monsoon, lasting from June to September, brings the majority of India's annual precipitation. This is preceded by the pre-monsoon, March to May, a typically dry, warm season associated with the hottest temperatures of the year, and it's followed by the post-monsoon, October to November, associated with cooler and less cloudy conditions, except over southeast India where you get northeast monsoon and most of its annual rainfall in this season as well in the southeast. The 4th season, winter, lasts from December to February. This is a wet season for much of the northern subcontinent, including the Hindu Kush, Karakoram and Western Himalaya (WH). For locations of these ranges and other important physical features of the region, we'll look at figure 1 pronto. As Western disturbances, an eastward moving synoptic scale trough embedded in the subtropical westerly jet, impact the region, bringing heavy rainfall to the lower foothills and plains, as well as heavy snowfall to the mountains. The Hindu Kush receives up to 80% of its annual precipitation during the winter, whereas the Western Himalaya receives a little less than half, with this fraction decreasing quickly towards the south and east. Okay, we'll see the figure for that as well. WDs differ considerably from monsoon low pressure systems, which mostly come from the Bay of Bengal into the core monsoon zone, even though some come up in the western eastern Arabian Sea and cross over to land. The other synoptic scale vortex is the LPS, or the low pressure systems that regularly affect the subcontinent, whose development and propagation is driven by moist thermodynamics coupled to the mean monsoon flow. Wow, that's a long topic, so let's not go there anyways. Let's read a bit about what are Western disturbances, just in terms of definitions. It's fairly clear, but once you call it a Western disturbance, you need a method to define it, to track it, to identify and track the disturbance, and so on and so forth. And so on and so forth is a lot. I say something that is not maybe necessary. Anyway, WD cyclogenesis occurs to the west of the Hindu Kush and Himalaya over regions such as the Mediterranean Sea. Cyclogenesis occurs as small scale disturbances in the jet grow into deeper troughs in the presence of baroclinic instability. Think of them as just vertical shear, if you may. Then they propagate as troughs embedded within the subtropical westerly jet until they reach South Asia. Early studies established that WDs move eastward at speeds of 6 to 12 meters per second, although they disagreed on their lifetime, usually because of the inconsistent definitions of genesis and decay. They typically fall in the range of 2 to 12 days. Lots of papers cited here that you can follow up with. Rao and Srinivasan detected an average of 6 to 7 WDs per month way back in 1969 during the winter season. In contrast, WDs are comparatively rare during the summer months. although more recent studies have discussed their importance when interacting with the monsoon trough, and there is a section on this in the paper, and I'll read a bit about that. Okay. WDs typically pass over Iran, Iraq, Afghanistan, Pakistan, and India, but occasionally make it as far as Nepal, as far east as Nepal, Bangladesh, and China. Their impacts are usually greatest over North India and the Western Himalaya, where they bring cold waves, fog, and avalanches, and where baroclinic interactions with the orography can result in heavy precipitation. Even with scarce in situ measurements, diligent use of observations, particularly upper air soundings and satellite data, means that synoptic scale WD structure has been well understood for some time. The presence of an associated upper level trough was first identified by Singh in 1963. Chitlangia in 1976 used a composite of 6 WDs to show that above the surface low, WDs are associated with vorticity, an ascent structure that extended through much of the troposphere, capped by a region of upper tropospheric divergence. If you have convergence at low levels and rising air, then it has to diverge at the top, obviously. Similar results were reported in subsequent case studies, Singh and Kumar, who further identified that frontal regions were sometimes associated with the passage of a WD, particularly in the upper troposphere. Furthermore, Rao and Rao observed that WDs were embedded in a region of strong vertical wind shear, from which they reduced their predominantly baroclinic nature. WD structure was progressively refined over the following decades as satellite. Oops. Why are you doing that to me now? Okay, something happened here. Okay, let me make sure I'm still recording. Yeah, I'm still recording. Somehow the laptop decided to throw me out and do something funky, but it is not letting. Yeah, here we are. Okay, so WD structure was progressively refined over the following decades as satellite data reanalysis and higher resolution models became increasingly available. The salient features of WDs, summarized by Dimri et al., which was the last review, and Dimri and Chelvutiri, are a strong upper level trough, i.e. geopotential height minimum, upper level trough, I hope that's what I said, embedded in the subtropical westerly jet, which is over the northern part of India during the winter. It migrates further south during the summer season, and we have an easterly jet in the summer sorry, let me get it right. In the winter it's not, let's just leave it there. Okay, which is there is a easterly jet on top because the lower winds are southwesterly in the summer monsoon season. So this is usually associated with a weaker surface low, sometimes with frontal features which can occur at any level but which tend to weaken as they approach the Himalaya. Broad ascent ahead of the system centers, often associated with heavy precipitation, and broad descent behind them, and strong vorticity at their center, peaking in the upper levels. So a lot of description there. If you don't follow all the words I'm saying, then please read the paper, but we'll look at some figures soon. Thus the dynamics of WDs sit somewhere between extratropical cyclones and mid-latitude upper tropospheric troughs. Their unique proximity to both mountains and a maritime moisture source, however, leads to a unique array of impacts that are not found in other regions. Key characteristics of the WD along with its environment are summarized in figure 3, and in the meantime I am getting another spam call that I'm going to ignore. Why are Western disturbances important? WDs are the dominant synoptic winter weather pattern over the Western Himalaya and surrounding region, and are associated with a wide range of impacts including cloudiness, rainfall, snowfall, fog, cold waves, and avalanches. Understanding their evolution is therefore key across all timescales from weather to seasonal to climate. Growing evidence also suggests that WDs are impacting the weather outside the winter, leading to extreme precipitation events, which we will discuss in section 3.5. So let's look at a few figures before we close out this podcast to make sure it doesn't go too long. The map of the Western Himalaya, Karakoram and Hindu Kush mountain ranges. So you're going here, orient yourself, Afghanistan, Pakistan, India. Let's not worry about the borders with all their disputes. Kyrgyzstan here, China over here, and down here you go into Bangladesh, Nepal should be somewhere up here, and so on. So Hindu Kush is here, Pamir's Karakoram range, Western Himalaya is what we call this region. Thar Desert is here, so that's northwest India. So you're going from about 60 degree east to about 95 degree east or so here, and you are going from about 25 north to 45 north over here. So this is the zoom in region, if you can see. Okay, this is climatological winter December to March precipitation over the Western Himalaya and Hindu Kush region. Mean winter precipitation here, you can see the scale, mean December to March precipitation in millimeters per day, going from 0 to over 6 or so. So there is the maximum and there is another maximum. So bullet points, obviously topographically driven maxima with shadow regions in the middle, and you have fraction of annual precipitation occurring during December to March, and this region gets almost 100% or at least 80 to 90% of its rainfall in the winter. Heavy rainfalls here account for 60 to 80% or so, let's say, of the winter of the annual precipitation. Okay, these are from ERA 5 reanalysis, so you have to be careful because they don't do so well on precipitation, and especially in the topographic regions, because the models that are used for reanalysis themselves don't have very good precipitation, but to the extent that they assimilate data, they are the best dynamically interpolated data we have. Okay, so here is the subtropical jet westerly. I don't know, Google Drive is complaining about something. Jet streak outflow, so here you are on the other side. So WB, the Western Disturbance vertical core with its eastward propagation, and here is India, Arabian Sea, and you have Pakistan, Afghanistan, Tajikistan, Kazakhstan, and so on over here. So a geostrophic descent. So this is the cyclonic vertical core with ascending motion, cold dry advection out, so sinking air and cold dry air advection out, and you get radiation fog over here with a mix of these descending air masses and low level cold air advection. A geostrophic ascent on the front of it and deep convection as well, and you have orographic ascent, and that's going to squeeze some precipitation because you have warm advection and moisture loading happening here. So we'll come back to this a little bit later. So this is the schematic outlining of some of the key meteorological features of WDs as they approach the Western Himalaya. The WD is characterized by a high vorticity region shown here in red, propagating eastward along the subtropical jet, which is in green here. It's associated with the transverse ageostrophic circulation, so including broad descent to the west and a broad ascent to the east. So you have some kind of a cell here, let's say. Within the latter area, the strong orographic ascent occurs along the mountain barrier of the Himalaya. Its outflow forms a jet streak downstream. So here is the jet streak flow here. So the interaction of the deep convection with the subtropical jet. The cyclonic circulation often also extends to the surface. So the WD is in the upper level, but you have the impact all the way to the surface. Northerly advection of cold dry air occurs to the west here, as we saw, which with large scale descent produces ideal conditions for radiation fog, and we worry about fog only when it's near the surface, of course. To the east, warm southerly advection brings moisture from the Arabian Sea. Large scale ascent, orographic forcing, moisture supply, and latent instability promote deep convection, resulting in heavy rain over the lands and snow over the foothills of the Western Himalaya and other mountains in the range. Okay, so this is already about 20 minutes long, so maybe that's a good enough length to stop here. Then we'll do the next part, which is on the structure, dynamics and thermodynamics, as well as the life cycle of WDs. I will read a bit of the summary of earlier research just for context, but in the other sections I won't be reading so much of that. There is also things on detection and tracking, track density, etc., but I will rely more on the figures to summarize the paper because the text is quite extensive. It's useful, but it's best done by reading, because if I try to read a lot of technical details, then you have to imagine everything in your head. Where is the ascent, where is the descent, where is the convection, and where is the orography, and so on and so forth. Okay, so see you in the next part of this podcast.